Everything we call real consists of things that cannot be regarded as real, declared Niels Bohr, one of the masterminds behind quantum mechanics and a Nobel Prize winner. Now picture this. One random afternoon, out of nowhere, your mental state flips. The world surrounding you stops feeling real. Sure, your arms and legs still move around, but it's like they belong to some futuristic prosthetic rather than your own body. You glance at the faces of people closest to you, and a strange fakeness clings to them. Even time and space start behaving like they've lost their minds, stretching and shrinking in a surreal roller coaster. Reality itself warps into something that feels distant and dreamlike, like you're stuck inside a dream you can't wake up from. If you're rolling your eyes at this, thinking it's pure fantasy, think again. Many, maybe most people experience fleeting episodes of this state at least a few times in their lives. So not having felt it yet doesn't mean it won't ever smack you out of the blue. In the 1999 movie The Matrix, the hero Neo is hit with exactly these same sensations, a deep, inexplicable hunch that the world isn't real. This mental condition goes by the name Derealization, and we still haven't pinned down all the nuts and bolts of how it works. But in Canada, the birthplace of the actor who plays Neo, it affects close to 1 million people per month. If you ever go through derealization, you realize how painfully tricky it is to describe. It's like our language isn't equipped with the words. Wikipedia gives it a shot. It may feel as if the person is looking at their immediate environment through VR glasses, through glass, or on a movie screen. People may report that what they see lacks vividness and emotional coloration. The emotional response to visually recognizing loved ones may be significantly reduced. The person may not even be sure that what they perceive is actually real. A key difference between hallucination and derealization is that in derealization, you're not suddenly seeing or hearing stuff that doesn't exist. Instead, what's really there just feels distant or dreamlike, often paired with déjà vu or its eerie counterpart, jamais vu. We've all heard of déjà vu, the sensation you've already lived through a particular moment or spotted it in a dream. Jamais vu flips that on its head. It's a jarring feeling that something familiar suddenly looks totally foreign, like you're seeing it for the first time. This can trigger a panic attack for some. If you ever notice derealization symptoms, try not to freak out. Odds are things will settle back to normal before long, because chronic derealization on Neo's level is thankfully rare. And let's not kid ourselves. The Matrix main character Neo isn't suffering from some random mental glitch. He's caught in a full-on machine-built simulation that sucks in every person on the planet. I'll be honest, this film doesn't exactly set my heart on fire. The simulation hypothesis has always felt a bit one-note to me, but there's no denying the Matrix is a cultural force of nature, one of the defining artifacts of modern civilization. Good luck finding anyone, even if you drive hundreds of kilometers into the middle of nowhere, who hasn't at least heard of it. On IMDb, the planet's biggest movie database with 500 million visits every month, you'll see it sitting at spot number 16. That's out of over 700,000 titles. And let's be clear, it's not just coasting on revolutionary action sequences and cutting-edge effects for its time. Head over to YouTube channels that dissect a film's deeper messages, and the Matrix discussions still top the charts, even now, a quarter of a century after it exploded onto screens. Before 1999, few people had any clue what a simulation hypothesis was. Then, the Matrix arrived, and it was like someone finally voiced the cosmic question that had been lurking in the back of everyone's mind. The film struck such a universal nerve that, frankly, most of us are a bit sick of hearing about it by now, which might mean there's something there after all. We still have no definitive handle on why derealization happens, but what if, like Neo, this bizarre state, which some sources claim most of us experience in passing, isn't just a warped perception, but points to something deeper? And if you think it's all hot air because, hey, even if we're in a simulation, we'll never be able to prove it, trust me, that's not entirely true. In fact, we've already found ways to prove things along these lines. Take the profile on Sam Altman in The New Yorker. He's the top dog at the company behind ChatGPT. Many people in Silicon Valley have become obsessed with the simulation hypothesis, the claim that what we perceive as reality is actually computer-generated. Two tech billionaires have gone so far as to secretly enlist scientists to work on taking us out of the simulation. But before they can yank the plug on this cosmic VR, they've got to confirm we're actually in it, right? How would you do that? Imagine you're a character in some elaborate video game that mimics our universe, at least enough to fool most of us most of the time. Now, how do you prove that code is behind everything you see? Let's find out. Let's go with something everyone knows, GTA San Andreas. Picture yourself as a character in that game. How on earth do you figure out you're living in a simulation? The obvious idea is to look for the edges. After all, San Andreas is basically an island surrounded by ocean. So you might hop in the fastest boat you can find, hit the throttle and head for the end of the world, except the map's only about 6 by 6 kilometers, and the game was never designed for you to sail halfway across the galaxy. But it's sneakier than it looks. There's no neat boundary or brick wall. You just keep on cruising away from the shoreline until you eventually starve to death. Suppose, though, you found some miraculous workaround so you never died of hunger and just sailed for 3 whole months in real time. You'd cover a distance equal to 50,000 times the game's map, around 300,000 kilometers, roughly the span from Earth to the Moon. At that point, the engine would be pushed into such a ludicrous corner that your character would start glitching to hell, splitting and contorting all over the game's space. It's impossible to say exactly how that insanity would look from a first-person angle, but if you were a character in the game observing it from afar, you'd have to wonder if your world had just gone off the rails. And sure, that wouldn't be a smoking gun that you're living inside a busted simulation, but it'd definitely leave you scratching your head. Now, let's line that up with our so-called real world. Earth is San Andreas, and space is our endless ocean. If someone built a spaceship that could keep on flying away from Earth forever, then, just like in GTA, some super remote distance might uncork a suspiciously wild anomaly that'd force us to question whether our reality is on the level. To understand where this is going, crack open Leonard Suskind's book, The Black Hole War. Susskind co-created string theory, so we're in heavyweight territory. First, imagine an astronaut dropping into a massive black hole. What happens when they cross the event horizon? That invisible boundary where nothing, not even light, can claw its way back out. According to general relativity, the astronaut feels nothing out of the ordinary at that moment. Crossing the event horizon is a non-event from their point of view, and that's part of what's so dangerous about black holes. The event horizon is intangible, always moving, and always growing as the black hole gobbles up more matter. You could orbit too close and not realize you've passed the point of no return. So from the astronaut's vantage, everything's perfectly normal until hours, days, or maybe weeks later, depending on how big the black hole is, when gravity finally crushes them near the center. But at the actual crossing of the horizon, our hapless space traveler is just chilling in zero gravity. Now for the crazy part. Picture someone outside with a telescope, watching. For them, the astronaut never actually crosses the horizon. Instead, the astronaut appears to slow down, like they're stuck in cosmic molasses, inching toward the horizon but never quite crossing it. Time gets weird near a black hole, and from the outside it looks like the astronaut just hangs there forever. But, Leonard Susskind says, that's not all. There's another layer so wild it defies logic. From the distant observer's perspective, the astronaut meets a horrifying wall of fire, the black hole's firewall. Made from Hawking radiation, this so-called firewall is unimaginably hot, basically infinite, and it incinerates the astronaut on the spot. But that conflicts 100% with the astronaut's experience of drifting peacefully into the black hole, feeling fine until he gets torn apart later near the center. Clearly, the astronaut can't split in two, so which story is right? Susskind and other top-tier physicists, including Nobel Prize winner Gerard Hooft, say both viewpoints are correct. Welcome to black hole complementarity, a principle that's as head-spinning as it sounds. The essence of black hole complementarity, I explained to colleagues, is that, as crazy as it sounds, both stories are equally true. We're used to thinking a person's either alive or dead, no in-between. But Susskind insists not to sweat it, because there's no way for these two contradictory observers to compare notes. The astronaut can't crawl back out of the black hole to wave, "I'm alive," in the skeptic's face, and the distant observer, by the time they realize the astronaut's been fried at the horizon, no longer has enough time to dive in and confirm it. This cosmic red tape blocks the paradox from blowing up in our faces, but that doesn't make it any less bonkers. A single event happens in two opposite ways, and both are somehow real. The objective meaning of the concept of the simultaneity of two events was lost in 1905, but the concept of events itself remains solid as a rock. If there is a nuclear reaction inside the sun, all observers will agree that it is happening inside the sun. No one will register that it's taking place on Earth. But something new is happening in the powerful gravitational field of the black hole that undermines the very objectivity of events. Events that a falling observer would consider to have occurred deep inside a huge black hole, another observer would register off the horizon, dissolved in the noise of Hawking radiation photons. And yeah, you might be thinking, sure, black holes are weird. Why are we blabbing about them if we started off talking about some monstrous anomaly you'd hit by flying away from Earth indefinitely? Because, as Susskind says, what happens around black holes is the same cosmic circus that plays out near the boundary of our observable universe. The universe doubles in size roughly every 15 billion years, so about 15 billion light years out in every direction. We've got our own personal event horizon, like a black hole horizon, beyond which everything's receding faster than the speed of light, thanks to the insane expansion of space. No signals can cross that boundary and come back to us. It's the point of no return, swallowing galaxies and stars, and who knows, maybe entire civilizations right this second. It's like each one of us is stuck inside an inside-out black hole. Don't think it's just a poetic metaphor either. The math spells it out. As something approaches that horizon, we see it slow to a crawl. Just like near a black hole, its light has to cross an ever-growing distance. And if you could string a thermometer all the way out there, you'd find the temperature ramping up, eventually hitting infinity right at the horizon. According to Susskind, if you could look across the cosmic void at a planet inching toward your horizon, you'd watch it roast alive in a searing wall of flame at the very edge. But here's the kicker. If that planet's got any intelligent life, from their point of view, they're perfectly fine, and it's us, floating near the edge of their horizon, who are getting roasted at this exact moment. How do we make sense of that? And what does it have to do with the simulation hypothesis? Hang tight. From this entire twisted saga, Leonard Susskind and Gerard Hooft draw some shockingly far-reaching conclusions. If, from a distant observer's standpoint, absolutely nothing ever crosses into a black hole, how in the world does that black hole increase in volume? The punchline? It doesn't. The black hole's volume is basically an illusion, since everything that supposedly goes inside is really just encoded on its surface as quantum information bits, as is roughly shown in this illustration. And what is true for black holes is also true for everything else, because anything can become a black hole if compressed hard enough. In short, Susskind and Hooft are telling us that the entire world we see around us might be a hologram smeared across the two-dimensional surface of the cosmological horizon. This isn't some fringe crackpot theory either. Holographic principles are a booming, influential area of research in theoretical physics right now. You don't feel like you are encoded somewhere on a two-dimensional surface for the same reason a cosmonaut falling into a black hole doesn't feel himself violently stretched all over a flat event horizon. Meanwhile, if you take string theory at face value, it goes even further. It places every bit of information, whether it's in a black hole or in black paint on a newspaper page, at the outer boundary of the universe, or at infinity if the universe has no end. Here's the conclusion T. Hooft and I came to. The three-dimensional world of our ordinary experience, the universe filled with galaxies, stars, planets, houses, rocks, and people, is a hologram, an image of reality encoded on a distant two-dimensional surface. This new law of physics, called the holographic principle, states that everything within some region of space can be described by means of bits of information located at its boundary. Bits of information? What the hell are bits of information? What the hell is encoding on a distant flat surface? What are we talking about here? Real objects or some kind of computer code? Here it is necessary to pause and say the following. In the process of narration, we'll sound very loud names of the most notable scientists of this and the last century. We're inching closer to the strongest arguments for the simulation hypothesis, and yeah, that might freak some people out. No matter how convincing you find these arguments, though, the simulation hypothesis still lives in the realm of philosophical discussions. Keep that in mind. John Archibald Wheeler was the kind of scientist who seemed to have his fingers in every major pie of 20th century physics. He co-authored papers with Niels Bohr, joined the Manhattan Project, and mentored a lineup of genius-level minds: Hugh Everett, multiverse theory; Kip Thorne, interstellar science mastermind; Richard Feynman, that brainiac we all know, and more. The very reason we call black holes, that's on Wheeler. The guy was a force of nature, and he also sounded the alarm that something seriously weird was going on around black holes. One day during a lunch at Princeton in 1998, I asked Wheeler what he thought would be the dominant topic of physics in the coming decades. He tilted his head, as he had done more than once that day, as if his aging skeleton was tired of supporting such a mighty intellect. Now, however, the pause lingered, making me question whether he wanted to answer my question or had forgotten about it altogether. But then he slowly raised his gaze to me and mouthed a single word: information. Wheeler believed that objects, matter and radiation, should be viewed as secondary, as carriers of a more abstract and more fundamental entity: information. He believed that information, where a particle is located, what its spin is, whether its charge is positive or negative, and so on, forms the integral core at the heart of reality. From this perspective, our universe can be thought of as an information processor. Brian Greene. Greene spells this out in his book The Hidden Reality, devoting nearly a whole chapter to the simulation hypothesis. That was a surprise for me. If the world's most famous string theorist is taking this stuff seriously, who am I to scoff? It sent me down the rabbit hole looking for more evidence. Turns out a bunch of heavy-hitter scientists toy with the idea that our universe is some kind of computational system, not necessarily built by a cosmic programmer, though some do lean that way, but computational at its bones. Edward Fredkin and Stephen Wolfram see reality as a matrix automaton, where a simple code yields mind-boggling physical complexity. Frank Tipler imagines the cosmos as a program, minus the need for an actual computer. Lex Friedman's all about the simulation hypothesis. Neil deGrasse Tyson once hosted the most viewed debate on the topic, and ended by saying he gives the simulation scenario pretty high odds. It's not just random basement talk, big names are in on it. It is not unreasonable to imagine that information resides in the core of physics in the same way that it resides in the core of a computer. John Wheeler. Where the hell did people get this wild notion that our universe itself is a computer in the first place? It all boils down to the Turing Principle, a fundamental law that makes virtual worlds possible. That is, the physics of the world allows you to build an object that can simulate any part of our universe. For example, your smartphone or computer is just such an object. And if you think about it, it's not at all obvious why that's possible. And by saying that the physics of the world allows you to simulate any part of the universe, we're talking about however large parts of that universe and however high the accuracy. Case in point, No Man's Sky, a 2016 video game that conjured up 255 entire galaxies, home to 18.5 quintillion planets, each with its own terrain, flora, and fauna. Visiting every planet for just a second each would still take you 585 billion years, 42 times the current age of our universe. That's the Turing Principle in action, and the rabbit hole goes even deeper. Because without this principle, we wouldn't just lose computers, we'd lose the very possibility of thinking beings. Every time you look at something or brood over a problem, you're running a simulation in your head. Picture your old school, and you've basically got one part of the universe, your brain, simulating another part, the school. Einstein did it all the time. He ran mental experiments long before anyone tried them out in the real world. That kind of imagination only exists because the laws of our world let us spin up simulations in the first place. No Turing Principle, no conscious minds, no life, period. Genes themselves are mini simulators of their surroundings, which is the entire concept of adaptation. Throw a random critter on a lab table, and you can guess its natural habitat from its body shape alone. Fish belong underwater, birds in the sky, monkeys in the trees. Even a single stray DNA molecule from some distant planet could reveal a goldmine about its alien environment once our tech gets good enough. Where it came from, the local star system, tons of cosmic dirt, all from a microscopic hunk of code. That's how life works. It runs an internal simulation to survive. Our entire reality is built to simulate itself, and that's why life can even exist. Life is the means by which virtual reality was first realized in nature. David Deutsch, theoretical physicist and pioneer in quantum computing. Long before the first computer ever flickered to life, some folks had a nagging suspicion our world was a grand illusion. But it wasn't until Oxford's Nick Bostrom dropped his bombshell paper, "Are You Living in a Computer Simulation?" in 2001, that science really started taking the notion seriously. This paper is so inescapable it's practically jammed into every single YouTube video on the subject. And it all boils down to a disturbingly simple argument. If humanity doesn't die out before it learns to build ultra-realistic sims, and if we don't outlaw them, then the odds we're not inside a simulation right this second are basically zero. Think about it. If there's one real universe but a billion fake ones, you've got a 1 in a billion shot at being in the original. That's exactly what Elon Musk meant when he said there's a 1 in a billion chance we're in base reality. But don't roll your eyes at Musk. He's far from the only heavyweight pushing this line. Take astronomer David Kipping, who crunches the numbers and says it's basically 50-50. Or Nobel Prize-winning physicist George Smoot, who ramps it up even further, claiming there's a 1,000,000,000 to 1 chance we're in a simulation. This guy even did a TED Talk titled, "You're in a Simulation and Physics Can Prove It." So why would humanity even bother churning out so many simulations in the first place? For research, obviously. Physicists, biologists, social scientists, they already hammer out billions of rough simulations daily. As computing power keeps shooting through the roof, those models will morph into freakishly realistic alt-realities. Scientists want to scrutinize the impact of life on cosmic structure, trace the course of evolution, map some big social phenomenon. If you're an anthropologist or a historian, or if you want to properly understand the rise and fall of civilizations, then you're going to need to do a lot of different simulations involving millions and billions of people. George Smoot. How colossal a machine do we need for that? And how the hell do we fast forward through centuries of data in one go? Well, Brian Greene says a quantum laptop could whip through the collective thoughts of every human in history in a fraction of a second. And that's not even the only bizarre nugget fueling the simulation hype. Never heard of the Fermi paradox? It's that big fat question mark over why our supposedly teeming universe seems emptier than a desert. Turns out the simpler explanation might be that life is just insanely rare. Back in the day, when we uncovered proof the universe is about 13 billion years old, biologists freaked out. They thought life needed infinite time to pop up. Billions of years was too short for something so wildly improbable. But we do have infinite space, with more cosmic real estate than you can wrap your head around. And that space might have coughed up a handful of needle and a haystack civilizations. The rest are so far away, we'll never glimpse a photon of their existence. But what if we really are alone? What if we're stuck in a simulation? Because simulating an actual infinite universe is impossible. If our universe isn't truly infinite, what would that look like? Fire a bullet from a rifle and drop another bullet next to it at the same moment. They'll smack the ground simultaneously. It's counterintuitive, but that's what Einstein's relativity says. Earth's mass warps space-time. Theoretically, the entire universe's space-time can loop around on itself like a sphere, but big-scale measurements show the universe is flat. That's suspicious as hell. Imagine if you stuck humanity into no man's sky. We'd eventually tally up precisely 18.5 quintillion planets in 255 galaxies. Sure, that sounds random at first, but then somebody genius level might point out that 18.5 quintillion is the largest unsigned 64-bit integer, and 255 is an 8-bit cap, so guess what, folks? We're inside a game. So, in our present reality, scientists have great suspicions about the huge number of numbers existing in the universe, and among them are the numbers associated with that very flat space. Physicist Max Tegmark says flat space is just some kind of miracle to make you understand the probability that the universe after the Big Bang will remain flat and not curve to one side or the other is much lower than if you flipped a coin and it fell not on one side or the other and the edge. To understand the depth of the scientist's surprise, here is a picture. The middle curve corresponds to our flat universe. And as you can see, changing just the last of the 24 digits by just 1 unit to one side or the other would cause the universe to collapse or, conversely, come to a big freeze without living even 4% of its current age. If you replace the 24 numbers with random values and solve Friedman's equation, the probability of getting a universe that remains flat after 14 billion years is less than for a dart thrown from Mars to hit exactly the center of a target on Earth. Yet the Friedman model of the Big Bang suggests no explanation for this coincidence. Max Tegmark. It's like the Big Bang was calibrated down to a hair's breadth. But seriously, if our universe is flat, how the hell can it not be infinite? Do we just slam into a wall somewhere and find a whole lot of nothing behind it? Don't even bother with guesswork. We actually needed a supercomputer just to crunch out what a flat yet infinite universe might look like. And let me tell you, it's bizarre as all get out. Think back to old school Pac-Man. Step off the map on the right, you pop up on the left. Exit at the top, you reappear at the bottom. The game's space is flat, but loops back onto itself. If we tried cramming Pac-Man's 2D board into our 3D world, connecting left to right, top to bottom, we'd get a donut shape, scientifically known as a torus. It's still flat, so parallel lines never cross and triangles keep their angles at a neat 180 degrees. But stitching those edges together, the way you see in the classic animations, requires a lot of bending and twisting. That warping would mean physics acts differently depending on which direction you look, and we don't see anything like that in our reality. All directions out there behave the same. So if our universe really is flat, yet wrapped up like a bagel, it'd be downright mind-bending. Reminds me of the movie A Beautiful Mind about mathematician John Nash. He proved it's possible to fold a flat torus into 3 dimensions while preserving distances between points. No one knew how that might look, but in 2012, a French team used supercomputers to figure it out. Surprise, our Pac-Man universe, shoehorned into 3D, would basically look like that wacky shape. Odds are, our own cosmos might be rigged the same way, giving us the false sense it stretches forever. Looking far out into space, we might realize that, for example, this very distant galaxy is actually our own galaxy, the Milky Way, whose light has simply made a circle around the closed universe. The data don't support this, but that's not surprising, because if our universe had artificial junctions, they would have to be located beyond the boundary of the observable universe, where light would never reach us. As Greene writes, simulated people on a simulated Earth would not get bored at all if the computer only modeled what is inside the cosmic horizon. And it's not just the far reaches of space we should be poking at, it's right under our noses too. If we're inside a simulation, and that simulating computer's resources are finite, then once we zoom in far enough, everything we see should be discrete, made of tiny, countable bits. Think of wearing a VR headset. Sure, everything looks smooth at a glance, but up close, you can see the pixel grid. Here's the kicker. Physicists like Greene are leaning toward the idea that reality itself might be fundamentally pixelated. Within the simulation hypothesis, That's basically saying space-time is one giant pixel grid. Zeno's famous arrow paradox lines up with this notion neatly. The ancient Greek philosopher claimed a flying arrow is actually always still, because at each individual moment in time, it's not moving. So if it's frozen at every instant, doesn't that mean it never really moves? Well, if space-time is indeed made of discrete slices or pixels, then under an absurdly powerful microscope, you'd see the arrow leap instantaneously from one pixel to the next, no in-between state at all, and at each new moment the arrow's frozen again. How long does a shift operation take in a processor? One clock cycle. What exists between those clock cycles? In terms of the shift operation itself, nothing. And what happens during the clock? Again, nothing in terms of the operation. Uniformity of motion in the real world can be an illusion, like in a movie in which the illusion of motion is created by rapidly changing individual static frames. In games, this is called FPS, which is frames per second. What exists between those frames? Nothing. The more powerful the computer hardware, the more frames per second the computer can draw. But the number of frames is still always finite. For a comfortable game, 30 frames per second is enough. And if you take a high-speed camera, you can easily see in slow-motion playback how instead of continuous motion, just static frames replace each other. However, as I discussed in my previous video, if you practice, you can distinguish individual frames with the naked eye even at 3,000 frames per second. But to summarize, in reality, the movement of objects can literally be caused by the fact that at the quantum level, they disappear at some points and appear at others. Zohari Davoudi, a theoretical physicist at MIT, and his colleagues even proposed an experiment to test this hypothesis. Space certainly looks continuous, but we tested this to a distance no deeper than a billionth of a meter. It is possible that someday, with more precise equipment, we will establish that space is discrete at a fundamental level. But for now, the question remains open. A similar, limited understanding holds in the case of time intervals. The discoveries that the information capacity of any region of space is given by 1 bit per unit Planck area are an important step in the direction of discreteness. Whether or not reasonable simulations will ever appear, I think we will indeed come to believe that this world is fundamentally discrete. Brian Greene. So here's the million-dollar question. What's our reality's FPS? And here's where even folks way outside the physics world start sniffing a rat. Because if there's one thing that screams hard-coded limit, it's the speed of light, 299,792,458 meters per second. We call it the speed of light, but really it's the top speed for anything in this universe. Anyone who's ever learned about this limit for the first time probably thought, wait, that's ridiculous. Why can't I just keep accelerating forever? Even seasoned physicists admit it's bizarre. It doesn't fall out neatly from the laws of physics we know. It's more like a fixed artifact, one of the biggest mysteries in the field. But in a simulation? Easy peasy. That's the processor's speed cap, the cosmic frame rate you just can't beat. When we, ordinary people, hear that the speed of light cannot be exceeded, that the speed of light is a constant, we usually do not realize how strange it really is. Picture yourself drifting in space near Earth, switching on a flashlight. Yep, you get 299,792,458 meters per second. Then, imagine Elon Musk blasting by at 99% of the speed of light in his Tesla, flipping on the headlights. You'd think that'd juice the numbers somehow, but nope. As strange as it may sound, even though he's flying at almost light speed, he'll get the same 299,792,458 meters per second, just like you. No more, no less. Wait, so if Musk on his Tesla flying past a stationary you turned on the light at the same time as you, what do you get? You'd think his beam would be nearly twice as fast as yours, right? But nope, nothing outruns light in a vacuum. And that's not just a tired cliché. Both of you record the same speed. How? Because from your vantage point, time in Musk's Tesla slows down. If you're clocking how far light goes in 1 second, roughly 300 million meters, you'll finish your measurement first, since you see his clock ticking slower. Then he swings back around to compare, and sure enough, from his perspective, his clock was always normal. Except it'll show less time elapsed than yours, or Earth's, or anything else that stayed still. So just to point out that of all of the above, there is only one thing you need to remember. The time of moving objects slows down. And that's weird, but not as weird as the fact that from the perspective of a moving object, all of space in the direction of its motion becomes shorter. And the higher the speed, the more the distance shrinks. This effect is called Lorentzian length contraction. For example, moving at half the speed of light, space in the direction of your motion will shrink by 13.5%. That's not sci-fi, it's a verified real phenomenon. Once we manage half the speed of light, Proxima Centauri isn't 4.2 light-years away anymore, it's 3.6. No, just think about it. The entire space of the universe is shrinking in your direction as you move. One more time, the whole universe shrinks in the direction of your movement. This effect is always there, even when you're shuffling off to the grocery store. The difference is too tiny to notice at slow speeds, but it's there, and once you hit near light speed, it's mind-blowing. The whole universe. I promise, that was the last time. It's just, how do you get something like that into your head? If you scream through space close to light speed, you'd see Proxima Centauri loom just 1,338 kilometers away. You could cover that gap in a lightning-quick 20 milliseconds, while anyone on Earth would insist 4 years had passed. And that's exactly where the "we're in a cosmic video game" crowd leaps in. Why is light capped? Why do we watch distances warp like taffy at high speeds? If we are in virtual reality, the limited speed of light, and all this schizophrenia with the compression of space, is explained very simply. In order to calculate the trajectories of interactions of objects moving at high speeds, the computer must perform more calculations. But if its resources are limited, it can only spend a fixed amount of computing power on all objects in the universe, no matter how fast those objects are moving. I've spent ages picturing how this might play out. Here's a wild scenario. In a racing simulator, the game pours most of its computing juice into rendering the car and its immediate surroundings. If it tried to model the entire map with the same level of detail at the same time, it'd run out of horsepower and bog down. Same as saying the game's clock would slow from an outside perspective. But from the driver's seat, would you feel the lag? Hell no, because your perception is also being crunched by the same system. You can't be aware of what's going on when the computer isn't giving you the resources to notice. From inside the sim, it's a seamless ride. So from the driver's point of view, the distance literally shrinks and time crawls from the viewpoint of anyone who's stationary. But for the driver, time flows perfectly normally. It's almost like that Zeno's arrow paradox, except the computer isn't filling in every single frame, skipping some points along the way. Real life might look smoother, but for all we know, that's just our crappy measuring tools failing to catch the gaps. And as nuts as that sounds, there's an even nuttier idea lurking behind it all. Namely, that our so-called reality might be running on limited computational fuel. I consider matter to be derived from consciousness. Max Planck, one of the founders of quantum mechanics, Nobel Prize winner. We can say that even if the universe is not infinite, consists of a finite number of points, and even if the laws of this universe do not allow anything to move at infinite speed, there is still too much unnecessary complexity in the world to be modeled. In video games, to avoid system overload, instead of modeling the entire game universe, objects outside the player's field of view may not be rendered until the player pays attention to them. Greene writes that the simulation, for example, can only model stars around the sun at night, and only when there are no clouds in the sky. The same is true for modeled cells, molecules, and atoms. For the most part, they will be necessary for the modeled experts of a scientific discipline, and only when those experts are directly studying these exotic worlds. Greene. This whole notion might sound like it belongs in a psychiatric ward, yet the foundation behind it is surprisingly solid. Think back to the famous double-slit experiment. If you try to catch a photon in the act pinpoint which slit it goes through, it behaves like a neat little particle, producing two bright stripes on the screen. But if you're not snooping, you get that wavy interference pattern that proves the photon had no single path at all. It was just a probability wave until you tried to look at it. John Wheeler took that idea to extremes. Behold the Hubble image of two quasars, except it's really just one quasar that's 9 billion light-years away. In between it and Earth sits a galaxy so colossal, its mass warps the surrounding space, creating a gravitational lens that can bend the quasar's light to the left or the right. That's your galactic scale version of the two-slit setup. If we rig a device on Earth to measure which path the photon took, boom, you'll see it choose the left route or the right route. 2 stripes on the detector. If you shut off that measuring device, you get interference, meaning the photon wasn't committed to going left or right for all those billions of years. In other words, your decision right now, whether to look at the photon, reaches back through time and dictates which side of the galaxy it chose, eons before the Earth even cooled enough for life. That's Wheeler's delayed choice experiment, proven in real labs on smaller scales and showing that measurement doesn't just record reality, it makes reality. Wheeler called this the participatory anthropic principle, saying that photons from a quasar, the quasar itself, and maybe the entire universe, don't fully exist without an observer to call them into being. In a paper celebrating Einstein's centennial, Beyond the Black Hole, John Wheeler offered a sketch of the universe as a giant U shape with an eye perched at one end. According to the caption, this symbolized a self-exciting circuit. The thin part of the U, upper right, expands over cosmic time until it eventually spawns observers, top left. Those observers then retroactively grant physical reality to everything, even the universe's earliest moment. And according to proponents of the simulation hypothesis, this is very similar to how in games the surrounding reality appears, that is rendered, only when the player moves his or her gaze there. Thus, a computationally less expensive copy of familiar reality that reaches the required level of detail and simulation as needed would be perfectly adequate. Greene. Wheeler was echoed by another famous theoretical physicist, Neumann-Wigner, winner of a bunch of awards, including the Nobel Prize. Wigner, reflecting on the strangeness of the quantum world, also believed that consciousness plays a key role in shaping objective reality. This interpretation of quantum mechanics was called the von Neumann-Wigner interpretation. And if you take this interpretation on faith, the idea that the universe is literally being rendered right before our eyes doesn't look so crazy anymore. The microscopic structure of the Earth's interior can be easily omitted. Remote astronomical objects can be subjected to a very high level of compression. Exact similarities need only be within a narrow range of properties that we can observe from our planet or from a spacecraft inside the solar system. On the surface of the Earth, macroscopic objects in habitable places may have to be modeled continuously, but microscopic phenomena can be made up for ad hoc, that is, as needed. What you see through an electron microscope should not be suspicious, but you usually have no way of confirming its consistency with unobserved parts of the microscopic world. Bostrom. Some people might shrug and say, okay, even if there are all these limitations, surely it's impossibly hard to simulate a universe as complex as ours. But what if it's not? Stephen Wolfram, for instance, argues that a handful of simple rules can spawn a system as intricate as the one we live in. Meanwhile, Max Tegmark has suggested that the fundamental equations of the universe could be surprisingly basic. Computer scientist Jürgen Schmidhuber even realized it's easier to write a program that generates every possible computable universe than to write separate programs for each. Think of it this way. How tough is it to write one masterpiece of world literature? Next to impossible, right? But how about writing every single masterpiece that's ever been or ever will be in human history? Strangely enough, it can be simpler. Back in 1941, Jorge Luis Borges wrote a story called The Library of Babel, which is about a huge library consisting of hexagonal rooms, each with 20 shelves, each with 32 books of the same format. All the books have 410 pages each. with 40 lines on each page. There are about 80 black letters per line, which allow 25 spelling characters, 22 letters, a period, a comma, and a space. There are no numbers or capital letters. What's the point, you ask? The point is that this library contains all books with all possible combinations of these 25 characters. This means that most of the books are absolutely meaningless, as they are a combinatorial search of all possible variants of 25 characters. However, the main rule is that no two books in the library are alike. Therefore, the number of books in the library is not infinite, but is 25 to the power of 1,312,000. This number is called the Borges number. And although the percentage of meaningful books of the total number is very small, nevertheless, such books contain absolutely all the text that mankind has created, all that it will ever create, and all that it will never create. As for the size of the Library of Babel, it would exceed the volume of the entire observable universe by a factor of 10 to the power of 611,338. Sure, if such a library existed. But the fact is, something like this does exist in reality. Take a look. It's a website with the telling name Library of Babel, which was created by writer and programmer Jonathan Basil, based on a story by Borges. The site simulates the Library of Babel to a certain extent. It houses 10 to the 4,677th degree of books. I can't even get that number to fully display in its entirety because it's a 1 and 4,677 zeros after it. Well, there are only about 10 to the 80th degree atoms in the entire observable universe. If you haven't figured out why I'm covering this yet, take your time. On the site, you can manually search through the books, or you can enter text up to 3,200 characters long of Latin letters, periods, commas, and spaces. And the site's algorithm will calculate and show you which room, which rack, which shelf, which book, and which page contains that text. There's even a 3D simulation of this monstrous library. I'll try to remember to drop a link. Roaming around it can seriously scramble your brain. There are Einstein's last words, which he whispered to his nurse before his death, but which she didn't understand or remember because she didn't speak German. You'll find the most detailed biography of every human, past and future, with all the juicy, scandalous tidbits. Cures for every cancer lie in there somewhere, along with formulas for eternal life. Possibly every stray thought you've ever had is tucked away in these endless volumes, not to mention the mythical code for Half-Life 3, that legendary game we'll never actually see. Some shelves hold a theory of everything, others hold ironclad proofs that such a theory can never exist. If you can dream it, any arrangement of letters, commas, and dots, it's already in the library. And in a sense, it was already there 10 years before I came up with it and wrote it. Creepy, right? But here's the real kicker. The library's brain-rattling complexity was conjured up with a pretty simple algorithm. By the same logic, our universe is just one among countless computatable universes, each one potentially spun from a tidy set of rules. And all of these worlds are probably generated by a short computer code, and that's the version of the matrix that Greene allows for in his book. Such modeled or simulated worlds would strongly support Wheeler's view of the primality of information. Create circuits that carry the correct information, and you create parallel realities that are as real to their inhabitants as our reality is to us. These simulations I will refer to as the modeled multiverse. Greene. There's one colossal red flag in our universe that, more than any of this other weirdness, should make you question if we're stuck in some glorified computer program. Take a hard look at galaxy rotation curves. They flat out tell us galaxies shouldn't even exist. All our models scream that galaxies don't have nearly enough mass to keep stars locked in their orbits. Those stars ought to be flinging themselves off into the void, and the missing mass isn't just a trivial shortfall, it's 500–600% more than we can account for. Instead of the nicely spinning galaxies we see, we should be looking at utter chaos. So the logical solution was to invent a name, dark matter, and pretend it's some phantom substance making up all that mass. But guess what? That's just a label, not an explanation. Nobody knows what it actually is, and we've been failing spectacularly for decades to find it. Under the simulation hypothesis, this headache is child's play to explain. The computer running our universe has limited processing power. Ever played Spore? It simulates Earth-like gravity for planets way smaller than Earth. Mass that tiny shouldn't create that level of gravitational pull, but the game does it anyway. The simplest hack for our cosmic simulation would be to slash the number of real objects in the universe, but keep the gravity turned up to match. Bingo? Now you know why space is mostly empty with ludicrous distances between celestial bodies. The emptiness itself might just be a convenient space filler for the Sim's creators. Among the oddities of the physical world nodding toward simulation is the so-called scale problem. The fact is that we use different laws depending on scale. Although Ernest Rutherford said that all sciences are divided into physics and stamp collecting, no one can actually say with 100% certainty that even the laws of chemistry are completely derived from the law of physics, let alone the laws of biology, psychology, or sociology. Here is what theoretical physicist Sabine Hossenfelder writes in her book, Existential Physics. At present, no one can deduce the properties of a cell from the properties of its atoms. In fact, even predicting the properties of molecules is difficult, as illustrated by the protein folding problem. The math is simply too complicated. If we can not combine the different scales of our reality, if the universe is like a patchwork quilt, sewn from different pieces that do not resemble each other, it will be a reason to at least think about it. As an example, the Sims 2 game uses different laws when going from the scale of a single house to the scale of a city, just the same. And if the characters within the game were reasonable and tried to combine these laws, they would fail. Simulators must address the inconsistencies that arise when different methods are used, and must ensure that entanglement happens smoothly. The entanglement may not be entirely effective. The inconsistencies that arise may build up over time, taking on threatening proportions, so that the world is inconsistent and the simulation collapses. Brian Greene. Even within known physics, it is not yet possible to unify the laws that are used on small and large scales. They're not just incompatible, they flat out contradict each other. Case in point, mash quantum mechanics with general relativity and you get an astronaut who's both alive and dead in a black hole. Perfectly sane, right? Then there's James Gates, a theoretical physicist who dug into the math underpinnings of our universe and found structures that look an awful lot like computer error-correcting codes. The only place in nature we see anything similar is in living organisms, where DNA plays error correction to keep us ticking. But here's the real showstopper, according to David Chalmers, the rockstar cognitive scientist and philosopher who was tapped to write an essay for the official Matrix website back in the day. If our world is just one massive simulation, then consciousness might be the biggest giveaway of all. The more we learn about the laws of the physical world, the further away we seem to get from cracking the mystery of our own minds. Here's what Max Tegmark writes in his latest book, Life 3.0. Talking about consciousness is not easy. If you mention the C word in a conversation with an AI specialist, neuroscientist, or psychologist, they will raise their eyes to the sky. If the person you are talking to is your mentor, they may take pity on you and try to talk you out of wasting your time on a hopeless and unscientific problem. Indeed, my friend Christoph Koch, the renowned neuroscientist who is at the head of the Allen Institute for Brain Science, told me how he was once discouraged from pursuing problems of consciousness until he had a permanent professorship and, it was no more, no less, Nobel laureate Francis Crick. If you look at what the article on consciousness in the 1989 edition of Macmillan Dictionary of Psychology says, you'll learn that nothing worth reading on the subject has been written. Consciousness might just be one of those things you can't wring out of any law of physics. Picture a crowd of people who've had their memories wiped and get shoved, courtesy of cutting-edge VR headsets, into the world of GTA 5. What would those people be able to understand about that world? Well, for one, they would have realized that there are laws in their universe that strictly govern the course of the mission. Here's the problem, though. Immersed in the game, people could have stripped the laws of the game universe down to its very foundations. Once they had access to the game's code, they could look through it down to the very last character. But they wouldn't find a line in there about being required to go on those missions. The game's prisoners would have discovered all the local laws of physics, the laws that prescribe the behavior of weather and water, the changing of day and night, and so on and so forth. But they would have discovered nothing that prescribed their own behavior. Their free will would be an artifact that is not deducible from the laws of the GTA 5 universe. The same problem may be true of our consciousness. What exactly is the voice we hear inside the head? This stream of inner speech that we speak to our conscious selves about. Does it arise only from physical processes, or does consciousness arise from a layer of reality that transcends the physical world? Greene. Absolutely no one knows if we will ever be able to simulate consciousness on a computer, because no one knows what consciousness is. Again, here's what the same Greene writes: perhaps for some bundle of connections to conceptualize in itself, it requires a substrate of convoluted wet matter. Perhaps if intelligent thought is meant to animate the inanimate, it needs the actual physical molecules that make up the brain, not just the processes and connections between those molecules. Perhaps the information processes going on in computers will always be different in some significant way from brain activity, which will prevent computers from being endowed with sentience. Perhaps intelligent thought is fundamentally non-physical, as various religions require, and so will always be beyond technological innovation. If it turns out you can't stuff genuine consciousness into a computer, that alone would demolish entire clusters of simulation hypotheses, Nick Bostrom's for instance. Still, that wouldn't snuff out every possibility. Maybe you're jacked into some Matrix-style rig, facing the lovely prospect that not everybody around you is actually alive. Maybe a bunch of them are empty shells, philosophical zombies, as David Chalmers calls them. These zombies are perfect down to the atom, act human down to the last flinch. But upstairs, there's nothing at all. You can stick a pin in one and get all the howls and tears you'd expect, but nobody inside is feeling squat. In other words, Agent Smith and the woman in red from The Matrix are textbook philosophical zombies. So keep an eye on people who clam up when talk drifts to consciousness. If it turns out we can run consciousness on a computer, then you're staring down philosophical nightmares that'd make a Boltzmann brain cry. Most folks prefer not to poke that bear, and I get it. Let's run one example. If space is infinite, anything not flat out forbidden by physical laws is happening out there. Anything, no matter how outlandish, repeats an infinite number of times. That means somewhere there's an endless sea of red dwarfs, those stars that can burn for tens of trillions of years. And if the laws of physics allow to realize the consciousness on the computer, then out of this infinite number of red dwarfs, there is an infinite number of red dwarfs, which feed with their energy through solar batteries the capsules with a powerful computer gathered as a result of accident in their orbit. And that cosmic kludge could be running, a Scorn-like game stuffed with fully conscious beings. Or skip the gaming angle, it could be a biblical-style hell sim with countless tortured minds. Given that a single star can last trillions of years, and a quantum computer might cram 1,000,000 years of thought into a second, the self-aware beings inside this capsule, their suffering would stretch for practically an eternity. It sounds like raw psychosis, but it is simply a direct consequence of the infinity of space and the realizability of consciousness on a computer. The optimist claims that we live in the best of all possible worlds, while the pessimist fears that this is true. James Cabell's famous phrase plays with new colors in such a context. I must stop here. I could go on listing artifacts that indirectly indicate that we are inside the simulation, but there is no need to do so now. We can't rule out the possibility that if we really are trapped in some souped-up VR, we might eventually blow the lid off it. Our brains are basically wetware rigs, forever spinning up internal models based on whatever data our senses feed in. Those models aren't the world itself, just approximations. Shoddy ones at that. Evolution didn't give a damn about us seeing the universe as it truly is. We see what's useful for staying alive. We think the Earth is flat. We're blind to curvature in space-time. We're dogged by optical illusions, misperceptions, you name it. And yet every time we set out to crack another cosmic secret, we end up discovering there's way more lurking just outside our bubble. We went beyond Earth to the solar system, then leaped to galaxies, then galaxy clusters, and who's to say the breadcrumb trail won't yank us beyond the entire known universe? Which leads to this bombshell. If there really are billionaire geeks bankrolling mad scientists to bust us out of the simulation, can they actually pull it off? Look no further than Hideo Kojima's 1998 masterpiece, Metal Gear Solid. There's a boss called Psycho Mantis who's become legendary. Mid-fight, this creep stops talking to your character and starts talking to you. In those old days, gamers had never seen that kind of meta trick. Psycho Mantis would psychoanalyze your playstyle, peek at your console's memory card, reveal which other games you've been playing. He even made your controller rumble and skitter on the floor. It was a mind blow, because suddenly it felt like he ripped right out of the game and was messing with the real world. He was unstoppable. He knew every button you pressed until you yanked out your controller and plugged it into a different port. That's the kind of reality hacking a mere game character managed to pull off. So imagine if we pulled off something similar. The real question is, what's beyond the game? Do we have bodies plugged into some cosmic VR rig like in the Matrix? Or is it all just code, with observers poking around from who knows where? Maybe the ones outside aren't even human at all. Maybe some far-flung alien lab is simulating the evolution of an entire universe, and we're just random side effects. Hell, maybe it's just the blank vacuum of infinity, because if space is unending, a spontaneously generated simulation computer is practically guaranteed to pop up eventually. We can't even guess. And some people argue we shouldn't try. In 2019, philosopher Preston Greene published an article in which he publicly urged that we shouldn't even try to find out if we're living in a simulation or not. To my knowledge, no physicist proposing experiments with simulation has considered the potential dangers of this work. Preston Greene. If scientists figure out we're stuck in a plain old real universe, we gain zilch. But if they suddenly discover it's all virtual, we might spark our own apocalypse. Why? Because if our entire existence is some cosmic sociology or history experiment, the real-world researchers only care about it while we accurately reflect their reality. The moment we wise up and realize we're lab rats in a sim, the experiment is worthless, and the plug gets pulled. This area of scientific research is full of assumptions and uncertainties, but one thing is for sure, if scientists continue these experiments with simulations, the results will be either extremely uninteresting or extremely dangerous. Is it worth the risk? So taking the red pill like watching this video can be very dangerous. I'm serious. You shouldn't be digging into this topic. I'm kidding. Let them shut it the hell down. There's also the chance we'll get blindsided by a cosmic blackout for no obvious reason, maybe because we keep poking around the universe's hidden corners, or because we invent artificial intelligence that triggers the endgame. Nick Bostrom, the guy behind the simulation argument, warns about what could happen once a truly advanced AI roars to life. In his words, a superintelligent agent may assign high probability to the hypothesis that it exists in a computer simulation model, and its perceptual sequence is generated by another superintelligent agent, resulting in a variety of convergent instrumental causes, depending on the agent's perceptions of what type of simulation model it might be most likely to be in. Translation: we have no clue how a godlike AI might act if it suspects reality is fake. Maybe it, like Psycho Mantis, will try to interact with the outside world in some way, and then the creators of our simulation will get goosebumps and will promptly shut it down. But hey, the simulation hypothesis is still just a shot in the dark, backed by zero direct evidence. Believe it or dump it. That's your call. Personally, I can't get over what quantum computing guru Dave Bacon wrote in What is Computation? For the most part, this is just another step in the direction of the claim that the universe is a kind of computer. This view has been advocated by many researchers, notably Ed Fredkin, Stephen Wolfram, and Seth Lloyd. In many ways, this view may be nothing more than a result of the fact that the concept of computation is a disease of our age. Everywhere we look today, we see examples of computers, computation, and information theory, and thus extrapolate this to our laws of physics. Couldn't have said it better myself. Anyway, thanks for sticking around. If some cosmic system admin decides to yank the cable, at least we can say we had one hell of a ride.